Thank you, Matthew, and I'd like to thank the organizers for inviting me for this interesting symposium. So I'm going to talk about whole brain effective connectivity as a biomarker for stroke. And I'm going to start with some background. And in recent years, resting state neuroimaging studies have really shown that focal brain lesions due to stroke can cause distant network-wide dysfunctions, which is typically in these studies captured by in terms of resting state functional connectivity. And this is very slow. And for example, in case of Siegel et al., they showed that two very robust biomarkers, or two robust markers, FC-based markers of acute stroke, irrespective of the heterogeneity of the lesions, etc., is the decreased functional interhemispheric homotopic functional connectivity and increased FC-legional inter-resting state network functional connectivity. And these low-dimensional alterations in the FC fit well with the fact that a few common factors can explain a large amount of variance across patients, as it was shown by Corbetta in 2015, in terms of different tests in behavioral domains. And they also correlate with model-based measures of integration and segregation, which was shown by our work. And they also show a correlated recovery with the corresponding recovery in behavioral deficits, as shown for spatial neglect patients by Ramsey et al. On the left, and some modularity changes as shown by Siegel et al. Last year. So clearly there is information in the functional connectivity to predict behavioral effects of stroke. But then there is more information in bold signals in terms of temporal information, which can be exploited using, as you probably have seen in this conference, by dynamic FC measures. And another way is to use effective connectivity, which is what I'm going to talk about. So effective connectivity, unlike the functional connectivity, infers causal or directed interactions. And several methods have been developed, including range of causality, partial correlations, and dynamic causal modeling, although until recently it was limited to mostly task scenarios, and it uses explicitly hemodynamic response function. The method that we used for this work was developed recently by Gilson and colleagues, which is essentially a multivariate Ornstein-Uhlenbeck process, which captures bold dynamics in terms of lagged and non-lagged functional connectivities. But key point here is that it forces the explanation of changes in the bold signals by anatomically plausible connections. So you estimate the effective connectivity for too fast. So the key ingredient in this method is the structural connectivity. So you estimate effective connectivity for some specific connections, and you optimize the model by comparing with the lagged and non-lagged covariances. And this method has also, Payares et al. Have shown recently that this method can be used to calculate effective connectivity of individual resting state scans of individual subjects. And it can be used to classify individual scans of individual participants. As you can see in the middle panel here, the within subject similarity histogram is quite well separated from between subject similarity histogram for the EC, but not so well for the functional connectivity. So my objective, our objective for this study was to assess if EC can be used to predict behavioral deficits or recovery using in stroke, and to identify biomarkers of these distinct classifications, and to be able to do some sort of prognostics where you can use information from early stage data to predict behavioral outcomes at later time. So I'm just going to quickly show the study design, which was used by basically in the study published by Corbetta in 2015. The advantage that we have is that we had a good sample in case of stroke studies with 132 first-time stroke patients, and they had resting state fMRI, behavioral, and DTI data at acute phase, which is 1 or 2 weeks post-onset, and 2 chronic phases, which is 3 months and 1 year post-onset. And so after in our case, we had data for 23 controls, 98 patients at acute phase, and 74 and 53 patients at chronic and chronic 2 phase. There was some attrition, not all patients show up for all phases. And behavioral scores of 7 factors, as I alluded to before, there were few factors that explain the variance across across patients. Also structural disconnectome and partial damage for each patient. And then we considered 2 classifications at all 3 phases. One was a diagnostic classification of controls from patients, and the other was just the classification of patients without any deficit, with a single domain deficit and multi-domain deficits. And a deficit in this case meant that a patient has a behavioral score of 2 standard deviations below the average control score. So we estimated the effective connectivity, and this is, again, as I mentioned before, the structural connections that you use to estimate the effective connectivity was important. So in this case, we used 2 structural connectomes. The first one consisted of 0.5% of the strongest connections that were present in the average structural connectivity matrix obtained from probabilistic tractography on the controls. And the other one was a deterministic end-to-end tractography atlas from diffusion MRI data from 842 HCP participants. And this was a much more sparser matrix, and ideally it would be useful, but it was not good enough. It was, I think, the edge density was 4%, and it's not good enough to estimate EC on its own, which is why we had to also use the probabilistic tractography data. And so for healthy controls, the mask of connections that we used to estimate EC was the same, but then from this mask, we had to remove for each individual patient those connections which were completely damaged. And so for individual patients, the mask of connections was an individual specific. And so the features that we used for classification were from the deterministic atlas, because that reduced the computational cost, but also these were the connections which were the strongest in the functional connectivity in our data set. So just a quick show that the fit between model and empirical covariances was quite high. And then we considered the classification of controls in patients, and in blue is the actual accuracy across the test sets by training the classifier on 80% of the data. And in orange is the chance level accuracy. And as you can see, both EC and FC showed significant accuracy in classifying or diagnosing patients from controls. However, EC did a slightly better job, as you can see here in the confusion matrices, where in chronic and chronic 2 phase, it distinguished controls from patients slightly better than the FC. Then we also calculated the biomarkers using recursive feature elimination with cross-validation. And we are still trying to figure out how to quantitatively describe the differences, but approximately about 200 to 300 features were identified, but only about a third at the maximum were common between EC-based and FC-based biomarkers in this case. So, in the interest of time, I'm going to skip this slide. But so then we considered the more complex classification of patients with different number of behavioral deficits in different domains. In the top panel, what you see is that I've used just the acute phase features to classify patients at 3 different phases, whereas in the bottom slide, I used the concurrent phase features. So the first thing to notice is that FC doesn't show significant accuracy in this case for any of the cases. Secondly, functional connectivity features from the acute phase not only classify the patients in the acute phase, but also in the chronic 2 phase, so 1 year down the line. And in this sense, I say that it is a prognostic biomarker because it can use information or it can extract information in the acute phase to classify patients at 1 year later in terms of behavioral deficits. And if you notice panel C and E, the mean accuracy of EC is much higher when you use the acute phase features than the concurrent chronic 2 phase features. And yeah, the confusion matrices also show this better accuracy, as you can see in the not only in the acute phase, but also in the chronic 2 phase, the upper right panel. The EC is able to distinguish between no deficit and single deficit patients quite well. By this time, there are not enough multiple deficit patients, and that's why the accuracy of or precision is low in that case. I'm not going to talk about this. Okay, so in summary, EC and FC diagnosed patients quite well, but EC turned out to be a better prognostic feature. It also predicted better than the chronic phase features. So I guess what I want to say in terms of this symposium for, if I could just move to the next slide. Yeah. So our approach has been to try to balance the predictability which comes from the statistical rigor and interpretability in terms of clinicians' interest and how they would like to do or plan the classifications. So I think I will stop here and maybe we can discuss more when we talk about questions.